Okay, so hello everyone. We're gonna try this again. I hope you enjoyed the rap beat that we laid out for you in the last video. I guess that was some sort of mic disconnection audio problem, and so hopefully it's resolved in this recording. I'll make sure to double check before I post the link. But basically, I just want to make sure to go over osmosis thoroughly because I do think it's an important process that I want you to understand from the perspective of physics, in particular because it's an entropy-driven process. And so that's why it's in chapter 14. And if you want more detail, I would highly encourage you to read section 14.7 and compare it to the last section in chapter 13 on diffusion, because osmosis and diffusion are often mixed up. They're often conflated when you're reading about them in biology and biochemistry. And I think by looking at the physics, you can kind of see where they are similar, but also where they're different. So to start us off, we'll look at this picture on the left, or sorry, on the right here. We'll get to the left a little bit later, but we'll look at this picture on the right where we have a region of volume where half contains a solution. So there's some solvent, presumably water, as well as some solute, maybe table salt or something dissolved in it. And the right side has, in this case, pure solvent, so pure water. So we have some concentration over on the left, and we have no concentration on the right. And in the middle, we have a special membrane, a semi-permeable membrane that only allows the water to pass through, not the solute. And I know this sounds esoteric, but it's actually very common, as many of you probably know, because cell membranes are an example of a semi-permeable membrane. They allow water to pass through freely, but other molecules, ions and macromolecules, have to be passed through specific channels, right? Ion channel, active transport, there are a whole host of things that cells can do. But the thing that they get for free is the osmosis, which is just the transport of the water itself, which is a smaller molecule that can pass through the membrane. And so the semi-permeable membrane is the primary physical distinction between osmosis and diffusion. So for osmosis, you have a system where the solvent wants to move to the side where there's solution. So there wants a flow from right to left in this diagram wants to happen. And when we're going through this section, it's important to think about why that is. We'll see why a bit more quantitatively in a moment, but just to tell you in words, osmosis is often misconstrued, and your book has a good section on this, but the actual origin is in entropy. So when the water is able to mix with the solution to spread out, that actually increases the entropy, so delta S is positive, and as a result, we get a more negative Gibbs free energy, right? Gibbs free energy is enthalpy minus temperature times entropy. And so as a result, we get a more spontaneous process, the more negative Gibbs free energy, meaning more spontaneity. And so osmosis is a spontaneous process that is entropically driven. So it's not due to an attraction between the water molecules and the solute, and it's not diffusion of the water. It's not due to a random walk or anything like that, because there's also water in the solution. It's on both sides already. So the random walk wouldn't cause a net flow. So it's not the same as diffusion. It's actually just the water wanting to mix with the solution in order to drive up the entropy to make delta S positive. And so in this diagram on the right here, we have the solution on the left, the water, pure solvent on the right, semi-permeable membrane in the middle, and then on either end, we have a movable piston. So we can apply a force on these pistons, and those forces are transmitted to the fluid. So we can apply a force Fr on the right side, a force Fl on the left side. And if we imagine those forces are being applied over the area of this piston, right? If it's a circular cross-section, it would be that force applied over a pi r squared type of area. Then we can define our pressures. So we have a PL, which is just FL over A. And if this thing is like a cylinder so that the area on the left and the right are equal, then we could define a PR with the same area, so just FR over A. And the way that we talk about osmosis, since it wants the liquid to flow, we can think of that as being due to a difference in pressure. So if you go back to the section on viscous fluid flow, a difference in pressure causes motion of a fluid. And so here we can think about the static situation. As long as we apply more force to the left side, so more force to the solution than we do to the right side, we can counterbalance the force that osmosis is producing, in a sense. And so here our PL has to be greater than PR if we want this solution to stay stationary. And we define pi, which is the difference in pressure, so PL minus PR, minus PR. And this is what we call the osmotic pressure, pi. And we'll see a formula for how to calculate it in a moment. But basically, it's telling you how much more do you have to push on the side with the solution than on the side with the solvent if you want this to stay still. If you don't push quite that hard, then the water will start flowing into the solution. And if you push harder, then the water from the solution will go to the pure side. So if the water is flowing into the solution, we call that osmosis. But if we push harder and the water from the solution flows to the pure side, we call that reverse osmosis, which is something that I think many people have heard about these days due to the prevalence of reverse osmosis water filtration. But as we'll see, that's a very energy intensive process because the forces involved due to this osmotic pressure are quite large. It's quite a big effect. Of course, the force is scaled with the area. So we should say that the pressure is quite large, but if we're thinking about something the size of a cell, the forces are pretty small. So watch out for that. And let's just go ahead and dive into actually calculating the osmotic pressure. So osmosis is an entropy-driven process. And like I said, it's due to this increase in entropy. So this is going to be a positive number due to the mixing of the solvent with the solution. And even though it's not required of you, if you want more information on this entropy of mixing, you can look at the last page of section 14.6, so right before the osmosis section, and it goes through a derivation for this delta S mixing. But entropy has units of energy per temperature, so we have to think about the dimensions in order to get a pressure. So first we multiply by T here, and that gives us a unit in the numerator of just energy. And then when we divide by volume, so energy joules divided by meters, this gives you a Newton, and newtons divided by square meters gives you a Pascal. So if we just did that all in one step and did energy over volume, we would get right to a pressure. So this does have the right units. And we can plug in this entropy change due to mixing that is derived in section 14.6. And that just gives you the number of moles of solute times R, the ideal gas constant. And then what we can do is we can take this number of moles over the volume and call that a concentration. Okay, so importantly here, the C solute is a moles per cubic meter. So the reason we know that it has to be moles is that we see this ideal gas constant. That's telling you that moles are going to be involved. You see R, ideal gas constant, in a problem, there's going to be something like moles involved because R is scaled by Avogadro's number from KB, Boltzmann's constant. And so we also have a T, not a delta T, so we have to be careful that this is in Kelvin. But the reason I point out the units of the concentration here is that in chemistry and in a lot of the homework problems and example problems, we deal with molarities, which is a moles per liter, and there are 1,000 liters in a cubic meter. So moles per liter is not the same as moles per cubic meter. So be sure to watch out for that as you go. Now, this is the formula if one side is our solution and the other side is pure solvent. But you might wonder what happens if there are concentrations of the solute on both sides, which is much more common. So if we have a Cl here and a Cr here. And so in that case, it's almost the same, but instead of C solute, we'll just have delta C. So Cl minus Cr. And so our osmotic pressure, pi, would just be delta C times RT. So hopefully pretty straightforward. But to give you some experience here, we can look at our first practice problem. So this problem asks, what is the molarity required of a 25 degrees Celsius solution in order for it to have an osmotic pressure of 1 atmosphere? So they tell us that this osmotic pressure that we want is 1 atmosphere, which in metric units is 10 to the 5th pascals, right? 100 kilopascals. They tell us the temperature, but we have to be careful. We have to convert it to Kelvin because this formula is using a T, not a delta T. So by adding 273, we get 298 Kelvin. And then we know the ideal gas constant, or we would be given it in an exam situation, is 8.31 joules per mole Kelvin. And so now we can just write down our equation. Pi is CRT, and we solve for C, so that's pi over RT. And we can just plug this in, and we get a concentration of 41 moles per cubic meter. But we're not done yet, because they want to know the molarity, which even though we just used the word mole, like I said, molarity is moles per liter. So we have to say 1 cubic meter is 1,000 liters. Now, I usually don't remember this conversion. It's just been on the tip of my tongue today since I'm repeating this lecture. But the thing that you should remember and just know off the top of your head is that a cubic centimeter is a milliliter. And so then what you can say is that 10 to the 6th cubic centimeters is a meter cubed, and 1,000 or 10 to the 3 milliliters is a liter. And so if you rearrange this, you can cancel the cubic centimeters and the milliliters, and you get this conversion factor of 1 cubic meter is 1,000 liters. Right, we can, just to clarify that, we can cancel this and this since those are equal. So at the end of the day, we're just going to divide by 1,000. And so we get our molarity is 0.041 molar. So if you're someone who has some experience in a chemistry lab, you probably recognize that that's a very dilute solution. And we also never talked about what it's a solution of. We just said it's a solution of some salt or some molecule, could be a macromolecule like a protein, that critically cannot pass through this semi-permeable membrane. That's the only condition on what the composition of the solute is. Everything else works the same because it's just thinking about the entropy of mixing. Okay. And in this case, what we see is that this small concentration is able to produce this huge pressure, 100 kilopascal, 1 atmosphere of pressure, which is quite a big amount, as we've discussed, which just goes to show you how strong osmosis is as a process. It really can move things, and our body takes advantage of that motion because it's free. It doesn't require burning ATP. It just requires some semi-permeable membrane, which are very common in the body due to cells, and some difference in solution concentration. Okay. Now we're going to look at another example in a moment, but I want to motivate it first. So now we're going to look at the left picture, which looks a lot like a capillary tube, but is different. Okay, it's a osmotically driven column of solution, and it can actually be of arbitrary radius. So it's hard to make semi-permeable membranes, so these are also usually small, but the radius, the area of cross-sectional area of that tube does not come into play when we're talking about osmotically driven water columns, whereas with capillary action, it's critical, right? We can only have very thin tubes if we want the fluid to be flowing up it due to capillary action. But in this tube, I want you to notice that we have the semi-permeable membrane at the bottom. So that's critical. And then in the basin, it's in this case pure solvent. And in the tube, we have pure solution. So the water wants to go from the solvent into the solution. The water wants to flow this way. And so there's a pressure difference, the osmotic pressure. And in order to stop it from flowing, we have to have something pushing down on this column of fluid. And what better force than gravity, right? We know that gravity exerts a pressure, rho GH, based on the height of some column of fluid. And so if this system is imbalanced, then rho GH has to equal the osmotic pressure. The osmotic pressure wants fluid to flow into the tube upward, and gravity wants it to flow out of the tube downward. So we just set those two equal to find sort of the equilibrium position. And we just saw that this osmotic pressure is CRT. And so we can easily solve for H. It's just CRT over rho G. Okay. And we reproduce that formula on this page, and we can immediately use it for an example. So most of these examples with osmosis will be pretty straightforward plug and chug type exercises. But if you've never seen them before, it's very confusing. And it's also just good to build your intuition around osmosis as a process. So here we want to know what height. So good, the formula is already solved for that. Does a dilute sucrose solution rise above a beaker of pure water at 25 degrees Celsius? Now, they don't say it here, but we have to assume that there's a semi-permeable membrane at the bottom of this tube, or this won't work. We won't get osmosis. The water and solution will just fall into the water and they'll mix together, which then will be diffusion. So diffusion doesn't cause a pressure gradient like osmosis does. That's a key distinction. So anyways, we know R, we're given the temperature, but again, we have to convert to Kelvin because these formulas just have T in them, not delta T. We know G is 9.8. Rho, so for a solution, the density in general is very tricky to solve for because when you add little particles to water, if you add ions to water, it could cause the water to come together and become more dense, or to spread apart and become less dense, depending on the balance of those forces. But for a dilute solution, it's basically just the density of water. So the effect, if you don't have very much solute, will generally be very small. So we can just take this density to be 1,000 kilograms per cubic meter. And then to get the concentration, remember that this formula requires that we use moles per cubic meter, and they give us a molarity. So what we have to do is we have to multiply this molarity, which is a moles per liter, by the conversion rate, 1,000 liters per cubic meter. So we're just going to move the decimal place 3 times to the right and get 20 moles per cubic meter. And now we just plug in. And if you plug all these values in, you should get a height of 5 meters, which is very tall, right? Over 15 feet. So like 2-story building-ish height. And that's telling you that osmosis is a very powerful force, yet again, as we saw in the last example. We can support an arbitrarily large in area, 5-meter tall column of solution, as long as we have a semi-permeable membrane at the bottom and pure water below it. So crazy, crazy. And this is why cells in our body take advantage of osmosis. So just to give you some examples, when we think about drinking water and hydrating our body, we're distributing that solvent throughout our cells, and that mostly happens in the large intestine. And so since our cells have more solute in them, they're the region of solution. And so an osmotic pressure develops that pushes the water into our cells, okay, until they reach some stability. The water is distributed. There are a lot of complex biological processes, but the basic absorption mechanism is osmotic. However, if you drink seawater or urine or something, with a concentrated solution, which people often do in survival situations out of desperation, then you actually have the opposite effect. The osmosis pulls water from your dilute solution in your cells to the concentrated solution in your large intestine. And so you actually dehydrate yourself. Your waste will have more water in it in terms of molecules than the water that you consume. So you make the situation worse. We also run into the language of like isotonic, hypertonic, hypotonic. This is just a way of describing the solution typically outside of the cell. So a hypotonic solution would be one with less solute than the inside of the cell, and would thus cause the water inside the cell to want to, it would cause the water outside the cell to want to flow inward to balance the two pressures, which leads to the cell rupturing. If you have a hypertonic solution, so more solute around the cell than inside of it, it'll leach the water out and cause the cell to collapse. So cells are constantly trying to achieve some equilibrium, this isotonic solution, and they have a lot of complex means that you would learn about in a biochemistry class to achieve that. And then one last thing, not related directly to osmosis, but it is related to the entropy of mixing, is to understand why oil and water don't mix. So oil and water don't mix, not due to some repulsion or something like that, but it's due to the fact that when you put a little bit of oil in water, the water molecules come and surround it. And when they surround it, you're minimizing the number of microstates. You're minimizing the number of ways the water could be arranged because the water has to come and surround the oil. And when you minimize or decrease the number of microstates, what you're doing is you're decreasing the entropy. So mixing a bunch of oil droplets in water actually decreases the entropy. And so when you have water and oil, they want to separate because that's actually something that causes the entropy to go up. So an important detail about osmosis is that, and this is something that sometimes shows up, is that the solution has to actually involve dissolving something. So it has to be a stable solution of the solvent and a solute. If you tried to do osmosis with oil on one side and water on the other, the entropy actually is already at a maximum. The system is already at equilibrium because they want to be separated. That's how we make the entropy the largest, and thus that's when processes that go towards that separation would be spontaneous, would have a negative Gibbs free energy. So watch out for that. Mixing, not always entropically driven. Sometimes oil and water, for example, you have a case where entropy causes things to separate. So this is why developing the language of entropy is so important. It helps us understand a lot of phenomena. I would highly encourage you to go through section 14.7 to see some more examples of this and to get some more practice as you go through the homework. So I'll leave it off here. Hopefully the audio quality is okay this time, and I'll see you tomorrow.